Yes, thank you very much, Gilles and Giulio, for inviting us to have this discussion session. So, as Gilles mentioned, this is an opportunity for you to also interact. So, Misaki has kindly gone through the heat to go to the village and buy some presents for those who will interact. So. uh, so the rule is, and the stick. So there are three levels. So there is beer for those who interact and give correct answers. Apparently there is Red Bull for those who try, but kind of not so great. Yeah, exactly. And for those who really maybe don't interact, the stick. Yes, so we will be discussing this topic. So I think I realized when we were discussing with Misaki and looking at the posters and discussing with you at coffee breaks, beach, lunch, you are all. I mean, most of you are working on more interdisciplinary topics. So we wanted to go back to, let's say, the core of the glassy dynamics. So in this school, as I was mentioning, we're no, I will put the stick down for the moment. In this school, we're interested in the statistical physics when you have a large number of entities that interact in the presence of disorder most of the time. So for some of you, these entities can be neurons. For some others, they can be spin glasses. Some more people might work on that. Some other entities could be, for example, firms interacting together, or animals in a complex food chain, for example. And what we've been learning also in the first lecture by Valentina and other talks is that most of the time, the fact that you have really a large number of entities and disorder gives rise to very complex landscapes in which the dynamics can become slow. So for those of you who do machine learning, for example, this could be the case. Actually, you don't work in this regime, but this is something very common to all these systems. And this is kind of the very old stuff, because people have been making glass for 1,000 years, maybe a bit less the kind of computer science. But what's really interesting is that the concepts and tools that have been developed in the field, including to describe these materials, have really influenced many fields. And you probably all know about it, but it's not something anecdotal. It's something that actually was awarded a Nobel Prize to Giorgio Parisi. But the people in the room here have also worked in close collaboration with him. So it's kind of an award for the field, I would say. And this is the title, but it's really the interplay between disorder and fluctuations in physical systems from atomic. So this is the kind of things we will discussing, to planetary scales, and I guess all this is kind of included in between both. So today we will actually go back to the real materials, so glassy materials, because the thing is that there has been a lot of explosion in all the interdisciplinary works, but the nature of glass itself, which sounds like something very simple, is actually still unclear. So we're going to try and explain a bit why this is the case and what we are currently doing, the open questions. So that's basically the goal of the discussion. And I will be doing more an introductory part, and then Misaki will discuss also what's going on in this topic at the moment. So let's start from the basics. So I understand that some people don't even have a physics background in the audience here. So this is probably very basic for many of you, but at least it's useful to put everything on the same page. So usually when you learn states of matter, I think you probably all have been to high school. So there is, there are three states. There's going to be the gas, the liquid, and the solid. Here are some kind of sketchy movies about what's going on. So the gas, very disordered and also very dilute. The liquid, you all have, I think, a very intimate experience of what a liquid is, water at the beach here. So if you look at the microscopic scale, this is very idealized water molecules, for example, still disordered like the gas, but the dynamics is still fast enough so that you can actually swim in it and it flows. And then you have the solids. So this is probably what you would put. Do you put ice in Red Bull? No, probably not. So if you drink a cocktail, for example, you will have ice, and here you see that there is actually a really dramatic change in the structure where the solids that we usually talk about are ordered. And all the transitions between these different states are pretty standard. They're standard phase transitions. We understand them very well. And the question is, what about glass? Is it a solid? Is it a liquid? Is it even something different? Neither this kind of liquid or that kind of solid. So this is really the kind of question that we're going to ask. And I mean, for some of you it might be trivial. I think the honest answer is still quite open, and we're going to go deeper into why this is actually very non-trivial. But to try and understand that, let's slowly recap how to make glasses in general. So in general, these are formed by rapidly cooling a liquid. So this is how, for example, window glass or this kind of arts silicate glass are done. So you take a melt, you heat it to very large temperatures, it becomes something very liquid. You can see here, you can pour it like a normal fluid. And then as you take it out of the oven, it's going to actually transform into something very viscous, and then at some point it stops flowing, and you call this a glass. So this is what you obtain at room temperature. So you see the dynamics is very different, but what about the structure? So if we could look at what goes on here, the question is whether these are different, because I think you would all agree that this looks more like a liquid and this looks more like a solid. But then if we look at the microscopic structure, is it similar to these crystalline solids? So this is the point where we have our first quiz in this discussion session. So these are, we'll describe a bit later, but these are 2D computer simulations. So these are configurations that Misaki obtained. So you can see that this is very idealized. Each particle is a kind of idealized atom. It's a sphere. And one of these configurations is a liquid and the other one is a glass. So does anyone want to, bet or try to win a prize on which one is a liquid and which one is a glass? And there is one which is a liquid and one which is a glass. Jaron, you want to win the second year, you want the alcohol, right? Okay. And the right one? The glass? Okay. So, okay, since you're more knowledgeable about glass, I'm going to make it a bit harder. Why did you reach this conclusion?
There's a couple places on the left one where I see some contact networks that are not, let's say, completely surrounding a given organ.
Mm-hmm.
So there's like some bonds that it's very suspicious that they're not filled by a
Okay.
contact.
But if we run a bit the movie, then these are going to equilibrate a bit. Maybe I mean, is everyone? Does everyone agree with Jaron? I think there's probably a way to win something. Yes. So Jaron. Wait, let's wait. Does someone disagree with Jaron? No one wants Red Bull, right? Sorry. A bit less dense. Okay. So the truth is, I actually don't remember. No, I think that so Jaron is right. The one on the left is a liquid, and the one on the right is a glass. But I think we can all thank Julia for participating. So you're wrong, but you participated. So you win a Red Bull. Okay, and you can. This is a liquid. This is a liquid in a solid that's a crystalline solid. It's a metal. But indeed, the difference is these are snapshots. I mean, Julia is fair. If you look at them, you close a bit the eye, not completely, because you still want to see something. It's really not clear which one is going to be a liquid or a solid, right? The structure is disordered. There's no clear structural pattern. That's really the whole point. This guy is flowing on a time scale which is very, very fast. Let's say it's a fast liquid, and this one would take the universe if you were to run the physical dynamics. So you see that still, there's a bit of. I think Julia, you could get a beer. Let's see later. So that's really the whole point about the glass transition. The problem is you see something with completely different physical properties, something flowing, something completely arrested, but if you zoom in, the structure to the eye looks very similar. So that's the whole difficulty of the problem, because in standard phase transitions from a liquid to a solid, you're expected to see a very dramatic change. You have symmetries that are broken, you have something very, very different happening. So trying to explain why this is the case is actually the whole point of the glass transition problem. So if I try to describe a bit what's going on here in a simple phase diagram, so for these liquids, so in both of your cans, you have at high temperature you have a liquid. It's disordered here. You can see that there's no arrangement. The point of cooling rapidly is that you want to avoid getting trapped in the crystal. So remember that this is a first order phase transition, so it actually takes some time to nucleate the crystal and for it to actually invade the system and transform into that guy. So in experiments, when you cool rapidly, you actually avoid the formation of this. And what happens is that you enter in a super cold liquid, so it means that it's like cooled below the temperature it wants to be a crystalline solid. So it's metastable respect to that, but it's still in equilibrium, still disordered, so basically it just looks like a liquid. But the thing is that the dynamics here in this blue regime is going to slow down dramatically. This is what you do when you take the glass out of the oven, and at some point it's just so slow that it's frozen. So it's just it's solid, it's a glass, and this is the glass transition temperature here. So when people were asking me, oh, what are you working on? I'm like, I worked a lot on glass. They're like, okay, great, but what about glass? I mean, it's kind of boring. But there's really much more than window glass. I think the word glass, in our life, it's just window glass, basically, or your glasses. But it's a family that's much broader. And the really cool thing with glasses is that you can make a glass out of anything, ranging from atoms. So for example, this is some golf clubs. So it's a company called Liquid Metal. So you can make metallic glasses, and they have physical properties that are super interesting. They're super bouncy. I wanted to put a video, but then I couldn't download it with the Wi-Fi. So the reason why they're super bouncy is that in crystalline materials, they're not always perfectly crystalline. You will have some dislocation, some defects. And every time they hit a surface, this is going to absorb some energy. But in these materials, this is a disordered system. There's no clear region where the system can dissipate, so it actually bounces a lot. So these guys do clubs, because I don't know if you do golf. I don't, but I guess this is something you want to really reach long distances. You can do molecules. This is the standard glass, but you can really make molecular glasses not just for windows, but for anything. And literally, I think in your smartphones you have some amorphous films. So glass is really everywhere. Also, you can make it out of larger molecules, which are polymeric. These are actually polycrystallines, but let's say they are glass. And then at larger scales, if you have colloidal particles, so these are small particles of around a micrometer, if you really compress them, it's similar to cooling, then you get a very dense paste, which flows on very long times, and this is also what's called a colloidal glass. So this is very, very generic, and I wanted to describe a bit more what the dynamic does. So when we really cool the system, to try and give some numbers on what we're talking about. So for example, this is an experiment on this molecule. I don't remember its name, but it doesn't matter. Here we will consider a cow is a sphere. Here, this molecule here is kind of a rod-shaped molecule. And so what you are interested in these experiments is to try and measure how the dynamics takes place. So what you can compute indirectly is the correlation of the orientation. So let's imagine at time 0, which is in log scale, so to minus infinity, you have the molecule placed like that. You're going to probe how it's reoriented, and this is supposed to tell you whether the liquid has flown in this region or not. So what you see here, it starts from 1, And at high temperature, which are on the left, it decreases, it decorrelates to 0. And this means that at this time, 10 to the 11, after 10 to the 11, the structure has completely rearranged. So it's a fast-flowing liquid. But as you decrease the temperature, you see that this curve extends to the right. And if you want to define a typical time scale, which is when it reaches, for example, this plateau, you see that it increases, and it increases in log scales. So this is really the more dramatic part. And at some point here, the glass transition, this is 100 seconds. So if you're doing an experiment and you wait 100 seconds, it's already quite long. And if you want to sample supercool liquid, so something that's in equilibrium, that's not a glass, you want to make sure that from the beginning to the end, you really have sampled new configurations. So you want this quantity to have completely decorrelated. So this is actually something that defines the glass transition, in an arbitrary way. So when the relaxation time is too long, then you're out of equilibrium and you transform into a glass. So some of the timescales I really wanted to highlight here. You have very, very fast, you have 10 picoseconds when the liquid is very fast, and it goes to 100 seconds. So that's really dramatic. And one way to reproduce, to show this in a more compact way is to plot this relaxation time. So again, the time at which this correlation hits a plateau. Since it's the same form, you can just take this as the relaxation time. And typically this is plotted in this plot here. So the relaxation time in log scale as a function of the inverse temperature. So why do we do that? The reason is simple, because if you expect to have a very simple process, which is Arrhenius, so if you imagine that the way the liquid flows is simply overcoming a simple barrier, you would have Arrhenius. So the people who are not there, but exponentielle E sur T. You would have something like an Arrhenius law. So when you take the log of this as a function of the inverse temperature in log scale here, you would get a straight line, okay? But in this, so that's why we typically represent it that way. It will become a bit clearer afterwards. And what you see is really this dramatic shoot up of the relaxation time. It increases by 12, 13 orders of magnitude when you change the temperature just a very little. Okay, so the structure doesn't change, dynamics is completely different. And again, here in experiments, we say that we arbitrarily define on our human timescales that the glass transition is when this time is 100 seconds. It's just too long, you don't want to wait. Okay? To give some ideas about what this means in practice, so this is some work that Misaki has done. So on the left, he showed some typical materials that you can all relate to. And this gives some idea about how viscous the liquid is. So typically the viscosity goes like the relaxation time. So here at high temperature, these liquids, all these molecules here, they relax like this olive oil. So it's quite viscous, but still very flowing. After you decrease a bit the temperature, it's already very different. It has the viscosity of peanut butter. I don't know what it is, but Nutella. So I know. So the viscosity of Nutella after changing just a little bit the temperature. At some point, you hit something like asphalt. So Misaki, you say it's one drop in 10 years. So you have this material, and it makes one drop every 10 years, so very different from the olive oil. And then at the glass transition, well, you have the glassy material. So really, when we say that it's dramatic, it's really dramatic. It's really the same material, you change a bit the temperature, and it goes through all these states. So that's quite spectacular. So we wanted to explain a little bit more this question of Arrhenius or not. And actually, all glasses are not, let's say, equally interesting or challenging. There are glasses that are called strong and others that are called fragile. So again, if we go in this Arrhenius law, so for example, for these strong glass-forming liquids, if you look at the relaxation time, so the time typically for a molecule to rearrange, it really follows an Arrhenius law with an energy barrier that doesn't depend on temperature. It means that, okay, the liquid slows down, but it's something that's really well understood. It's simply that you have an energy barrier to overcome, and well, you get something Arrhenius, and that's completely fine. And as a matter of fact, silica, which is let's say, broadly speaking, window glass is this kind of strong glass former. There's another class which is much more interesting and also very, very broad, which are these fragile glass formers. And this is what I showed in the past slide. So here what you see is that as you cool the temperature, in this log tau 1/T, you don't have a straight line. You have something that is increasing. So it's as if you had an Arrhenius dynamics, but the energy barrier now increases when the temperature decreases. So the E here, the apparent activation energy, is the local slope. So you see that at first it's not so large, and then it increases, and at some point, well, you hit the glass transition. So this is the kind of things that we are mostly interested in and that are really complicated to understand. Because it means that if you have an apparent energy that's increasing, it kind of suggests that you have something very collective going on. So somehow, probably at high temperature, you just need to go over a simple energy barrier, very small, and then as the temperature decreases, you need to move larger and larger piece of sample, so this is increasing the energy barrier. So this is something that we're going to come back to during this discussion session. In addition to, yes? So this barrier, so SiO2 and also this GO2, I think they're network forming liquids. So compared to all the other molecules which are completely disordered, these have a tetrahedral arrangement that they prefer, and this gives rise to a network. And I think we understand well that the energy barrier is related to, you know, breaking this network. And so I'm not 100% sure that all the strong glass form liquids are network forming, but at least in these cases, this is what happens. And the others don't form preferentially a network, it's just random packing. Yeah, no local order. Also, again, feel free if you have questions or things that you want to ask or interrupt. It's completely fine. So here, up to now, I've been discussing about relaxation time. So a bit as if there's only one time scale that dictates the behavior of the liquid. But this is really not the case because there is something that is called dynamic heterogeneity, which really characterizes these very slow liquids. So on the left, again, maybe a larger system, but you see this is a static structure. It's a computer model. You have all the small atoms, all the small particles. Again, if you look from far away, you don't see any particular correlation in the statics, and the structure is really homogeneous. But now, if you look at the dynamics, I'm going to show here what happens in the dynamics, but I'm going to show it in a specific way. I'm basically going to show whether locally the atoms have rearranged, so whether they flow or not. So if they don't flow, they're blue, so that's comparing time 0 with time 0, so nothing has moved. And then if they're red, it means that they have undergone some flow. So this is the movie that you obtain. So these red regions are the regions where it flows, and these blue regions are basically solid, okay? So I think that you would all agree that compared to the static, where you don't see anything particular, in the dynamics, you really have something extremely heterogeneous, with some regions that move very fast, so these regions, and some others like this one, which move very slowly. So this is the concept of dynamical heterogeneity. You have some regions that are fast and some regions that are slow, and 2 alpha is just the average of that. So you see that it's not the whole picture, but just a small part. And again, we wanted to really highlight that this is not an unusual phase transition, because if you think about standard critical phenomena, you look at the static structure. So for example, this is an Ising configuration with plus and minus 1. You see in the static structure, you see that is something. There is a structural, there is a static length that's diverging. You have a time scale that's diverging. This we understand very well. But here I showed you that there's apparently no static length scale, and diverging time scale, maybe not diverging, but at least I showed you that it increases very, very rapidly. So this is very different, and we need new tools and ways to understand that. So I also wanted to explain something on the dynamics. So if you look at the dynamics, I showed you this movie at a quite low temperature, where you see some very very vivid pattern in terms of the regions that are moving and the ones that are really solid. But actually, this changes a lot with temperature. So at high temperature, when the liquid is still very fast, you don't have so much heterogeneity. And then as you cool the system, you get some length scale, which is describing the dynamics, which increases. And this is something that you can also measure both in computers and simulations. And the way people have been doing that is via this 4-point function. So I'm introducing this now because Misaki will talk about it in a kind of recent model afterwards. So if you want to know the heterogeneity, what you can do is, I plotted the correlation function. It's something that decreases on a time scale that's changing. But if you want to know a bit more about that, and in particular some length scale, you look at the fluctuations of this quantity. And actually you get this kind of curves. So this is this 4-point function. So why 4 points? Well, C of t is already comparing the structure at 2 times, time 0 and time t. And when you look at these fluctuations, what comes out are basically 2 different points in space. So this is why we call this 4-point correlation. So this 4-point correlation as a function of time. Here, these are simulation results. But as you cool the system, you see that the peak, which basically corresponds to this 2 alpha, here it peaks around 2 alpha, you see that it shifts to the right, which is the system just slowing down. But you see that in addition, you have the peak that grows in size. And actually, you might accept this for now, but this is the peak value corresponds to the volume over which the dynamics is correlated. So I was showing you just before here, this dynamic length scale, basically the value of the peak tells you how large these domains are. So you see that as you decrease, you really have this length scale that increases for the dynamics. And you can also, in this plot here, I'm showing results for many different systems, so simulation system, experiments, which are all super different, glycerol, salol, I mean, you name it, there are a lot here. And this is the peak of the 4-point function. So this is the correlation length, the dynamic correlation length, as a function of 2 alpha. And you see that, in fact, they all kind of overlap on this curve. So if you rescale a little bit, so it means that this dynamic length really is intimately related to how slow the system is. Okay, so Misaki will also come back on maybe trying to explain why you have this curve here. And you also see that if this is a proxy for dynamical length, here you have a time scale that's increasing, a length scale that's increasing, but you don't see any divergence in this length scale here. It actually looks like it's saturating. So we don't have something diverging or anything, and the numbers you see are quite small. So this is the end of the first part on, let's say, introducing the problem that we have with dynamics, why it's complicated, why it's different from what we know in other phase transitions, and the big questions that are in the field and that are still open actually. Well, the first one, why do supercoliquids become so slow? So this is, why does a liquid transform into a glass? This is still an open question, and in particular, despite no change in the static structure. So really, it's quite mysterious. Even if you go a bit, below in terms of details, the way it becomes slow is non-Arrhenius. It's super Arrhenius. So also trying to understand what gives rise to this barrier that seems to increase with lowering the temperature is also an open question. Why do we have these dynamic heterogeneities? Again, is this glass solid or liquid? Is it something also new? There is this nice review actually exploring this question, and Misaki is going to explain a bit better what we mean by a new state of matter. So in the end, the question that we want to answer is this very viscous liquid just a liquid with a high viscosity? Is the glass actually something that reflects a true thermodynamic phase transition? It's not clear, but if so, what would be the other parameter? So we discussed about static changes. I showed that there's not much going on, so it's actually really non-trivial. And so this is a slide that Misaki put up to describe all the different scenarios and theories. Not all. I think many different theories and scenarios. So actually, many things, many theories, many scenarios have been put up. It's quite an old problem. You can see some of the papers are from the 90s. So there are different theories with completely different ingredients. So the first one and the second one, Misaki will talk about the first one in the next part. I will discuss a bit more the dynamic facilitation one. But basically, this theory says this has a thermodynamic origin, and we're going to describe a bit better what is the order parameter and everything. The second is, no, this is purely dynamic. We don't care at all about the thermodynamics. It's something purely dynamical. There are other kind of theories. Gilles Tarjus in particular put forward these frustration limited domain theory. So just to give a brief idea, even if the liquid is disordered, there are some locally preferred structures which look more crystalline, let's say here, these closed packed regions. And this theory tries to explain that eventually these cannot tile the whole space. So it's a bit like the liquid wants to crystallize or to have these locally favored structures, but actually it doesn't tile space. So this frustration can explain the slowing. I mean, it's related to the slowdown. So you see that's one quite static origin. Another one is these elasticity scenarios by Yepe, Dur, and Anaël Lemaître, where essentially if you see at very low temperature what's going on is the liquid is trying to flow in a matrix that's very solid. This is, what you've seen in the movies. And essentially, the matrix around is becoming increasingly stiff as the temperature decreases. And this is what explains the dynamic slowdown. There are other considerations. For example, here, Tanaka and collaborators have these more geometric considerations. So again, if you look at this structure, what you would see is locally there is some preferred six-fold symmetry. So this red region is more crystalline-like. And they claim that actually there is some critical-like fluctuation of this local order, and this explains the relaxation that's slowing down, and etc., etc. Yes. Yes, you can. Here you can see it directly. So they're saying, despite people claiming that there's nothing in the statics, actually if you really look carefully, then you find what you're looking for. So here comes our second quiz, which is the correct one. It's probably worth to mention that some people have actually, it's not like separate boxes. People have hopped from one to the other over time. So does anyone want to? A beer for Silvio France. Yes, Kini? Sorry? Okay, so you had the hand up at the same time as Silvio, so a beer again. Do we have enough beer? So if there's not enough beer, we will, it will be a kind of bon, and then we will give it later. Yes, so indeed, which is the correct one? Well, I think one thing is that the domain, we are more newcomers than some other people. Some people, recently died and everything, so it's kind of dynamic. No, sorry. No, sorry. Yes, Gilles, bien. Just to say that I think the domain has maybe this is this recorded? You can cut, okay. No, but I think I'm not well placed because you guys, many of you, the organizers, the speakers, have been in the domain for a long time. But it's true that the domain has, I think, had a lot of hot debates, including because of personalities of people, kind of clashes. I think it really pushed people to really look into what they were saying, to really try to put forward really good reasons to push forward one theory versus the other. But it's true that there has been a lot of debate, and actually I will show you towards the end that there is still some debate. So if we move to the trying to understand a bit better, so this is the relaxation tan as a function of the inverse temperature. The points here are for one molecule, but whatever. And all these curves here, all the different colors, corresponds to maybe what you can get by a theory or by a scenario, some phenomenological arguments. You get some prediction for how this should scale with the temperature. And basically you see that all these functions, which have completely different origins in terms of microscopic mechanisms, they all equally fit well, right? No beer for that. This is a result. We can say that they all fit well equally. So it's really hard to understand what explains this dramatic slowdown, because, for example, you can see that basically any theory that has reasonable ingredients will work. So we really need something more microscopic to try and understand how and why the liquid slows down along the way here. So this is where yeah, I will go ahead, but I'm trying to see. So this is where I think, so Misaki and I have been doing some simulations, many other people, but this is maybe why we are asked to describe this. The reason why numerical simulations are very interesting is that if you look at the experiments, what I showed up to now are mainly experimental results. You don't have access to the motion of all the atoms and all the molecules. I mean, it's quite obvious that these are way too small, so you cannot access them. And it means that most of the time you will have something very averaged. You have no idea about locally what the regions of the sample are doing. You have this very little spatial information, and it's quite clear that if you just look at averages, then you're not really going to able to distinguish between scenarios. So you need computer simulations. The really cool thing is that you generate the trajectories, so you have them, I mean, by default, for all times, for all particles, and it means that literally any observable can be computed. On this observable, you can have this multi-point correlation that I've just described. You can have atomic resolution for any observable. You can do very crazy things, and Misaki will describe some of the crazy observables that you can compute in the simulations. And really compared to experiments, I mean, experimentalists do an amazing job, and it's really complicated. They have limitations, but they have also great results. But in simulations, the nice thing is really the sky is the limit. I mean, all the settings are flexible, everything is well controlled. You know, one very complicated thing when you're an experimentalist is you measure something and the question is like, really, why do I see this? Is this an artifact? Is this because of this or that? The thermostat is not working, whatever. But in the simulation, except if you don't code well or there's a bug, but this is the job of the people doing the simulations, then you can do really anything. So you can change the microscopic model, you can change the shape, the size of the atoms, you can do molecules, you can decide your interparticle interaction, you can decide what dynamics you give to this set of particles. How are you going to simulate this? MD, Monte Carlo, we're going to discuss that. It was mentioned yesterday in the previous discussion by Elizabeth. You're not restricted to our dimensions, so we can do experiments in 1D, 2D, 3D, but it's hard to do 4D, right? But in simulations, people have been doing simulations up to 13 dimensions, so it sounds a bit extreme, but actually now I think it's become clear in the school that as you increase the dimension, you become more and more mean field-like. So it actually makes a lot of sense to do that. So this is also very informative to see how you go from our world to mean field in a continuous way. And also the system size can be varied. This is very useful to check how things depend on system sizes, the length and everything. So first, there's supposed to be a red box. So first we will focus on the microscopic model. So I showed you in the plot, try to convince you that this glass transition happens for anything, atoms, molecules, colloids, whatever. So let's choose the simplest atomic model, right? I mean, we want to simulate on the computer a model that's as simple as possible, simply because it's going to be cheap to simulate. Like if you have some very fancy molecule, if you try to simulate this molecule with here. If you try to simulate this molecule, and for each molecule you have all these atoms, it's going to take forever to compute. But we're really interested in something very universal. So we do the simplest thing to take atomic-like particles. So what we simulate are these spheres, basically. They all have a position that's Ri. We pick different diameters because we want to frustrate crystallization. If they all have the same size, you're going to find a crystal, and we're not interested in a crystal. Then you can define an interaction potential. So again, we choose the simplest thing pairwise, and then you can go from the simplest thing, which is a hard sphere. So basically, whenever this guy touches, it's infinite energy, and they don't interact if they don't touch. So this would be like billiard balls. You can take some more smooth potential, like this one here, but you can really change all these ingredients. And of course, the total potential energy is going to be just the sum over all the pairs of interactions. So if you're interested, there is this book by Dan Frankel and Berend Smith. It's really, I mean, for me, it's a Bible. For you too, for Misaki too. So I mean, if you're interested in the details, we really recommend it. It's very good, and there are others. Now, if we move to the second part, so we have our model, simplest atoms, different sizes, very simple interactions. Let's pick the algorithm. So the first one is molecular dynamics. So the idea of molecular dynamics is really to simulate the dynamics of the system and mimic what's going on in the experiments. So in the experiments, you put the atoms, they interact, they have like physical interactions, and the dynamics just takes place. So molecular dynamics simply consists in solving Newton's equation. So you have different particles, they interact, they all receive, they all have an interaction potential, and they feel a force which derives from this potential. And essentially, I'm skipping the details here, but it's solving for each particle this thing iteratively in time. And this gives rise to this kind of movie. So this is a very slow liquid. You have all the particles in 3D, and then they're all feeling the forces from the neighbors, and it's just solving Newton's equation, basically. So this is the physical dynamics. So let's look at what happens for this slowdown in MD simulations. So now we don't have orientation anymore. We have spherical particles, so we just look at how much they move over time. And if they move a lot, then this correlation goes to 0. So again, this correlation as a function of time in log scale. When you decrease the temperature, you have something similar to the experiments. You have this time, typical time at which it reaches this plateau, which increases logarithmically. So if you take for each temperature the time scale here, you get this kind of plot, again, Arrhenius. So this is the state-of-the-art data. So this is some simulation by Misaki and his co-workers. So this is the relaxation time, log scale again, 1/t. You see that this has this banana shape, so it's not a straight line. This is a fragile glass former. And you reach these time scales where the relaxation time is around 10 to the 5. So I think this is time for another quiz. So the quiz here is, in these simulations, we have this typical curve. So we go to the point where we run out of steam. So this corresponds to the last point that we can simulate, because then it takes too much time. And the question is, how far are we from the experimental glass transition? And if you want, I can probably help a little bit. So how many decades has the liquid slowed down here? 6. And in experiments, how many decades is it from with very fast liquids, 10 picoseconds, up to 100 seconds? 12. Okay, so how far? You have the burger like very far. I think it's a correct answer. I like this kind of qualitative answers. Okay, okay. We will find something to give you over the summer school. So indeed, yes, we are 6 orders of magnitude away, 6 decades away from experiments. So essentially, if you could continue here 10 to the 6, you would reach 10 to the 12, and this is the experimental glass transition. So it means that the liquids that, maybe that's a bullet, okay. If we move to the next slide, which makes it clearer, here you have the relaxation time. In experiments, this is setting, what's a glass. So in experiments, when 2 alpha is 100 seconds, this is a glass. But in simulations, if you do 1 week simulation time, which is already, quite long, this is our 100 second, basically, you reach only 2 alpha of around 10 microseconds. So it means that the computer glass transition happens here. So at temperatures that are much, much higher than what you have in experiments. And okay, you could say, well, great. Well, since the glass transition is defined arbitrarily, my arbitrary decision for computers is here, and this is fine. But actually, it means that you're not being able to observe how the liquid slows down 6 orders of magnitude more. So you can investigate what's going on here, but this regime is not accessible, and this is really where it starts to get interesting. Okay. So, as I said previously, the sky is the limit, so we're not limited in the computer to do physical dynamics. So MD runs out of steam very easily. So let's look at something else. Let's try to sample equilibrium configurations. So now the purpose is a bit different, not looking at the dynamics, but trying to sample different configurations. And to do that, we will investigate Monte Carlo simulations. So the idea of these standard Monte Carlo algorithms in the case of particles is the following. Instead of solving Newton's equation, what you do is that at each time step, you pick a particle randomly. So in that case, this is the central particle. And you try to displace it by a random amount in a small box around the particle. And then you compute the difference in energy, delta U, before and after doing this move. And you use the Metropolis filter, so you accept or you reject the move with a probability which is the mean between 1 and exponential minus the energy difference divided by t. And so let's see a bit what goes here. So if the energy decreases, the mean is 1, so you're going to accept all the time. But if by chance, for example, this particle overlaps a bit with its neighbor, so it increases the energy, you don't reject, you accept, but just with a weight that's proportional to what you want in equilibrium, which is given by Boltzmann. Okay, so you do that, and then n trials, so you have n particles. Essentially, you do that at random. It means, in average, you do it 1 time per particle. This is 1 Monte Carlo time step. So the idea of, then if you read our favorite book, basically what you learn is that this algorithm converges to the Boltzmann distribution, the equilibrium distribution. So what you are sampling are equilibrium configurations. So let's look at, again, what happens when you use this kind of dynamics. Well, you start to know the story now. If you look at the density correlation, it's basically the time scale increases. And again, if you look at the relaxation time as a function of 1/t, now the time is expressed in Monte Carlo step, but whatever, you see exactly the same shape, and then you also become dead at around 10 to the 6, so it means that you cannot really go below what you could do with molecular dynamics. So let's try something else, and people have been trying for a long time, and we're going to try one more thing. Let's try to sample equilibrium configuration, so not dynamics, but I think, Silvio, you get a beer if you kill the mosquito. Ah, too bad. So let's sample configurations, but with other moves, because displacing a particle is a bit like solving Newton's law, so it might be not so surprising that it doesn't speed up, but let's try and do something else, a new move, and that's, for example, in this case that we're going to discuss, it's called the particle swap Monte Carlo. So you do the same thing as before, so whenever you want to try a move, you pick at random between 2 things. Either you do the standard thing, so you try to displace the particle, or you do a particle swap. So remember, the particles have different diameters to avoid crystallization. So you pick 2 particles at random, you try to exchange their diameters. Again, you compute the energy before, after, you do the Metropolis filter, so you're sure that you're in equilibrium. And then it means that you're also sampling equilibrium configurations. So I think you would all agree that this is kind of a very small perturbation to the initial algorithm. Let's look at what happens in time. So again, this isn't physical, but at this point, we're not interested in the physical dynamics. We just want to get equilibrium samples close to TG. So here, this is particle swap Monte Carlo compared to normal Monte Carlo. So this is a relatively low temperature. So if you look at the correlation function for this temperature in the normal algorithm, basically you actually cannot really decorrelate. So you see that at time 0 and then after a week, basically the structure is very similar. If we look at the movie, you get something like that. So the different colors are the diameter of the particles. Small guys are blue and big ones are red. So you see that essentially, well, there's temperature, things are shaking, but there's no real rearrangement. So after a long time, you really stayed in the same configuration. If you turn up this very small thing, which is doing the swap, this is what happens. So sorry, I mean, I hope you don't have like epilepsy. I mean, it's quite. I think it's. You can see that it makes a big change at least. So the particles now can change their size, and this really relaxes much easier the structure. You see that same temperature, you switch on the swap, and then maybe the relaxation time would be around here, and now it's like orders of magnitude before. Yes. So it's 20%. So you do 20% swap and 80% of displacement. Yes, you could, but then, okay, you can do whatever you want. It's just that you have an optimum in terms of how much, how much this time it decreases, there's going to be an optimum. And okay, you're going too fast, but I think it's an open question as to why 20% gives the right mix of changing the diameter and displacing. I think it's really interesting as to why this is the case. If we go even below, so very, very low temperature, close to TG, if you were to run the normal MC, you would get a plateau, so really nothing moving. Really nothing again. And yeah, and now you add swap, and boom, you can really relax. So something that became impossible to sample, so you basically get stuck in the same place, really relaxes. So this is quite dramatic. And this is summarized here. So again, the same plot, the relaxation time as a function of 1 over temperature. Now the top regime is the 10 to the 5, because this is where we cannot run simulations longer. So standard Monte Carlo, you get this increase. And now for the same temperature, you put swap on, and boom, you get a massive reduction of the time scale. And it means that you can get this branch here in red. So you can equilibrate on all these temperatures. And you see that this is really dramatic, because if you were to extrapolate this up to way longer, 10 to the 12, you would get here. So this is the estimated experimental glass transition. You see you completely break this glass ceiling, how people call it, and you can go even below. So this has been something quite recent. You see 2017, where Andrea Ninarello, Ludovic Berthier, and Daniele Koslovic really put the right type of model with all this optimization to get this speed up. Yes? Any particles. So people have tried different things. So too close particles or really far away, and it doesn't change too much. So yeah. So you see the increase is massive. So it's 10 orders of magnitude at TG, and in 2 dimensions it's even more dramatic. It's 40 orders of magnitude. So something really immense. So I think this is the last quiz. Do you have quizzes? Yeah. No quiz. Oh, so this is the last quiz. So if you want to win a prize, this is now. So this is our last quiz, which is, why is swap so efficient? I'm not sure. Because it's non-local. Misaki, what do you think? No, it's a Yeah, definitely a beer. Yes, yes, definitely a beer. So actually, this is a quiz, but this is an open question. So we were hoping that maybe someone finds the answer. But I think this is the way people are thinking about at the moment. So why is swap so efficient? And in particular, does the fact that swap something that is actually non-local? I mean, local in the sense, it's non-local because you swap particles far away, but locally it's very local. What you're doing essentially is either inflating or deflating a particle. So this is very local. And you see that it kills the slowdown really dramatically. So there's even a question about can we actually learn something about why the liquid is so slow? You do something, it's very small perturbation, and then you kill 10 orders of magnitude. So you're like, okay, what are these 12 orders of magnitude made of? So does it tell us anything about the glass transition? So this is my last slide before we move on to Misaki. I'm going to try and show that there is still some debate in these recent years. So Viard and Kate say, yes, this tells us something about the glass transition. Bouchot, Biroli, and collaborators, sorry for naming, but are wrong. And Misaki you will understand a bit better. It means that they are wrong, and the title of their paper was "Does a growing static length scale control the glass transition?" And then a few years later, no, WC. So this is the acronym that is used in the paper to describe Viard-Cates. So I let you. I let you interpret. Maybe this choice instead of Viard and collaborator. But WC conclusions are incorrect. So basically, these people claim that the fact that swap works means that the way some people feel about the glass transition and the origin is wrong. But in fact, you see the same title. Does a growing control, can the glass transition be explained? So I think it's a bit broader and a bit broader and more open in terms of question. But in fact, there is still a lot of debate also based on this. And here is the sketch. So you definitely own your beer. The way we think a bit about it, but it's still very open, is in fact when you use MD, you're trying to go over energy barriers, and the swap basically allows you to go in other ways. So now you open a new direction, which is this diameter space, and maybe this is a way to go from one configuration to the other, following a very different path. But again, this is very open. Yes. Yes. No, so there's different ways to think about the swap. So either you think you're translocating particles, which is very unphysical. Another way, which is actually very equivalent, is to think that you're locally inflating or deflating. So you change the diameters, but the identity of the particle is the same. So it means that you're actually, in addition to giving positional degrees of freedom, you have an extra degree of freedom is how much I can breathe, basically. And this is one direction of research. Yes. No, yes, yeah, exactly. So the swap is just if you want to keep the same, okay. If you want to keep the same distribution of diameters, the simplest thing is to swap, because then you are not affecting anything. But then there are some works that have been trying to use this continuously, like changing continuously the diameter, or either actually adding a thermal bath. Like it's as if you look at your particle and you imagine you have a bath and you can just exchange from the exterior. And Federico Ghimenti, who's sitting next to you, is actually the expert on this kind of swap and collective swap. Yeah, you're surrounded. Yes, Grore. Okay. Yes. Yeah, it's like boom. So, Misaki, it took 1 hour, but it's okay. I finished. agree.
All the difficulty is that ordinary Monte Carlo flight is extremely hard to solve.
Yeah, but I well, okay, this is the open question point, the really open thing. I know, for example, what you've been doing with Federico, but for example, if I may show some kind of movies about what's going on. Wait. This is an internship that I was supervising, so it's trying to look at how the swap Monte Carlo dynamics goes on. So if you look at, allez, wait, if you look at normal Monte Carlo, you know we were this. No, it's sorry, it failed. I don't have the right movie. If you look at the normal Monte Carlo, you really have, you know, the dynamics that I was showing with the strong heterogeneity is super heterogeneous. But if you look at the dynamics with the swap, well, basically it looks different. So I know with Jorge we've been trying to discuss about what it means, but basically if you look at the movie at a very low temperature with the swap, présentation, activer le mode plein écran. So these are the particle motion at very low temperature. So I think, Jorge, you say, so sorry, this is a bit more expert-like, but you say that basically this looks just like normal dynamics. I have some image of it. So what we're what we're discussing with Jorge and so his work with Federico and other people is so on the left here, this is a displacement map with normal Monte Carlo. So you see something similar to what I showed with the blue-red region. So you have all regions that are not moving, and then some regions that are moving, and they're really moving a lot. Like these displacements are really many different events that go on. And on the right, this is so much lower temperature, but the same slowness in the dynamics. So this is high temperature, but with normal dynamics, so slow. This is very low temperature, but with SWAT dynamics, so typically the same slowness. So you see the average displacement is the same, but what I'm trying to put forward and trying to really understand is how the swap allows you to get this kind of, getting out of the initial configuration, and the way it does this is something super correlated and super coherent. So this is what we're trying to understand, and really trying to understand even microscopically why do you have these super long coherent moves. But I think Jorge's viewpoint is that actually this is just the very beginning, but if you look more at 2 alpha, the maps will look the same. Yeah, so open question. It's just the XY, yes. I'm not showing how much the particle has changed, yeah. But this is possible because the particles are changing, so it's kind of, changing all the landscape and everything, so yeah. Sorry, yes, Misaki is saying. I guess this is the picture which you just played. Yes, exactly. This is the picture we have in mind. Okay, so I think it's time to move to, actually, it's a nice transition to move to the open questions, and now Misaki is going to talk a bit more about this.
Okay, second part. So in this second part, we are going to discuss more recent work, let's say. So as Camille said, there are many theories and scenarios trying to understand the nature of glass transition, dynamics. So as Silvio said, maybe or probably we don't have the one correct theory. Instead, we have sort of combination or hybridization of a scenario in them. So hopefully in this discussion session, we can understand better. Okay, so first I'm going to explain briefly the random first order transition theory. So this is quite a popular theory in this community because it is related to also the computer science, machine learning, this kind of stuff. And this theory is inspired by phenomenology of in a class of spin glass models. So roughly speaking, there are two important temperatures. There are actually many other temperature, but let's focus just the two. The one is mode coupling dynamical transition temperature. And the other one is ideal glass Kautzmann transition temperature, TK, two temperature. So in this random first order transition scenario, the most natural quantity to look at is configurational entropy, or complexity that Valentina introduced yesterday. So basically, we wish to characterize a rough free energy landscape. Okay. Then we want to count the number of metastable state n, and the configurational entropy is defined by logarithm of number of metastable state divided by the number of particles. Okay. So at high temperature, so you have a many metastable state. So that's why a system can explore very quickly, so in a liquid state. But with decreasing temperature, the number of available state decreases, hence the configurational entropy decreases. And if you decrease temperature further, at certain point, you don't have, you have just one metastable state or sub-exponential number of metastable state. So this point is called the ideal glass transition temperature, or Kautzmann transition temperature, TK. And below TK, you have a ideal glass. So why we call it ideal? Because in practice, we cannot see this. So I will explain later. But this random first order transition scenario is justified, verified at infinite dimension, mean field limit. So this is good news, and this can be a good reference starting point of discussion. Okay. How about finite dimension, 2 dimension or 3 dimension in our world? The first, the mode coupling transition temperature is no longer a sharp transition. Instead, it's just a crossover. Okay? And also, we cannot measure configurational entropy in equilibrium below the experimental glass transition temperature that Camille introduced. Because typically, experimentalists can wait up to 100 seconds. If the relaxation time goes above 100 seconds, the system goes out of equilibrium, so we cannot measure configurational entropy. Therefore, we have to rely on crude extrapolation, maybe in favor of Kautzmann transition, or completely avoided smooth landing toward zero configurational entropy. So this is current status. Okay. Nevertheless, random first order transition theory is very useful to understand the nature of glass transition. But what is the appropriate order parameter describing glass transition? Okay. As Camille said, if you look at just a snapshot, the configuration, it's hard to see some sort of order from single configuration. Okay. So we have to think about this. The first easy example is liquid to crystal transition. So here I show liquid configuration at high temperature, above melting temperature. We have amorphous random configuration. So here I show crystal configuration below melting temperature. You see that you can detect some sort of order, crystalline order from a single one configuration. But in the case of liquid to glass transition, since liquid and glass are almost same, well, by just looking at the eye, so you cannot detect order by just single configuration. Instead, we have to see many different configurations. And what we see is actually detecting order among different configurations. That is called overlap. For a liquid side, above a Kautzmann transition, if you prepare many configurations, all of them amorphous, but if you overlap, they are very different because liquid can explore many different configurations. Whereas in the glass state, if you make overlap, they are very similar because in the glass state, the system is stuck in one metastable state. So therefore, the overlap is the correct way to look at glass transition. Okay. So now we have an order parameter for glass transition. How about Landau free energy? Because in a standard critical phenomena phase transition, so the Landau free energy as a function of order parameter is very useful to describe phase transition. So we want to do same things for the glass transition. So this is actually what France and Parigi constructed. That is now called France-Parigi potential, as I can show here on the left. So at high temperature, so we have a single minimum here. And this minimum corresponds to the liquid state, so zero overlap, okay? But with decreasing temperature, so we start to see second minimum here. And this second minimum corresponds to glass state, but still the metastable state with respect to liquid. Then if you decrease the temperature further, a certain temperature, actually precisely Tk, this minimum touches x-axis. So this corresponds to the ideal glass transition. Okay. So I have two more comments. The first temperature below which this metastable state appears is monocoupling dynamical transition temperature. And also this height, basically the free energy difference between a liquid and the glass state corresponds to T times configurational entropy. Okay. This is nice. On the right, I show the expected mean value of overlap parameter as a function of temperature. At high temperature, as I mentioned, overlap is there in a liquid state. But below Tk, you see a discontinuous jump of overlap. So this is sort of first order like transition. Okay. However, as you can see, this entropy plot, entropy doesn't show jump, so no latent heat. So this is, so it means that it's not a standard first order transition. So that's why people call it random first order transition. Okay. So this scenario is verified, as I mentioned, at the mean field limit, infinite dimension. But in real life, 2 dimension and 3 dimension, we are not sure whether the ideal glass transition exists or not. Okay. So in the case of finite dimension in 2D and 3D, so we have a spatial structure. Okay. So in that case, we can measure sort of static correlation length scale using overlap function. I'm not going into detail, but so as I mentioned, if you look at static structure, so it's hard to detect some sort of order by just looking at I, but by using some overlap analysis, we can look at the spatial profile of overlap function. And at high temperature, it decays quickly, but with decreasing temperature, it decays very slowly along radial direction. And we can extract sort of static correlation lengths. But again, if you look at by looking at I, it's hard to see some sort of order. Therefore, people call it amorphous order. Okay. And I want to mention that also Jorge Kusha and Rob Levin has another perspective in terms of amorphous order. Okay. And what we can find in finite dimensional simulation is growing static correlation length with decreasing temperature, as expected from a random first order transition scenario. Okay, so to conclude, in terms of thermodynamic aspect, so for the mode coupling temperature, so this is not phase transition anymore, so it's just a crossover, but still useful. So I don't mention in this seminar, but we can interpret mode coupling crossover as a sort of vanishing of saddle mode, saddle in a rough energy landscape, etc., etc. So it's still useful. For TK, as I emphasized, we cannot reach ideal glass transition temperature in the bulk system. That's why people call it ideal. But so nevertheless, many people, including me, worked hard about trying to, verify the thermodynamic prediction by random first order transition theory. So in particular, we performed extensive simulation and external field conjugate to the overlap function, and also confinement, which is called random pinning, etc. So we have many good numerical data consistent with random first order transition. So the next obvious question is, how about dynamics? Okay. So in a nutshell, random first order transition predict that this relaxation time scaled with exponential of this shape. So the static correlation length with some critical exponent psi. And our thought predict that this static correlation length diverges toward ideal Kauzmann transition temperature. Consequently, the relaxation time diverges toward the Kauzmann transition temperature. So it means that the origin of slow dynamics comes from singularity of the Kauzmann ideal glass transition. So this is very beautiful scenario. But in practice, we cannot reach the ideal glass transition, as I emphasized several times. Nevertheless, we can get some good understanding about, for example, the fragility of glass forming liquid. So as Camille mentioned, that one of the remarkable features of glass forming liquid is that the viscosity or relaxation time show non-Arrhenius behavior, this kind of banana curve. So this means that effective energy increases with decreasing temperature. Okay, so the R thought gives you prediction that, okay, as you can see, this effective energy is scaled with basically the size of static correlation length with some power of psi. So when I saw this prediction, I was very happy and I was quite excited. But according to recent work by Camille, so it's not simple. And I want to pass this next to you.
Yes. So indeed, Misaki just explained that this random first-order transition theory, in finite dimension, it predicts essentially that if you want to move the system, you have to relax chunks of the system that are the size of this static length, like collectively, and this length increases, so this is what drives the slowdown. So this means that the slowdown is really from this thermodynamic static origin, but actually there's another kind of theory, so the second one in the slide, which is more dynamic facilitation theory. And if we push this argument to the extreme, basically the picture here is that the glass transition is purely kinetic and it has nothing to do with thermodynamics. So it's kind of the two opposite extremes, so you can see where the hotness of the debates come from. And in fact, I don't want to go too much into the details, but this has been, put forward and showed in some kind of models, which are called kinetically constrained models. And there is a review, so Cristina Toninelli and her co-workers worked a lot on that. But let me just give you the essence of these models. The idea is that instead, in this kinetically constrained model or the facilitation picture, what you have is instead some defects, so something very punctual instead of something like a static length, very point defects which carry the mobility. And the structure of these defects is very stupid. They have, it's an ideal gas of these defects. No thermodynamics, nothing interesting. But yet, these defects can move in the system in a very constrained way. So their dynamics is complicated, but their statics is trivial. So I'm showing here a simple model for our kinetically constrained model in 1D. So here you have space, so this is x and then time, so it's a space-time map. And the black points corresponds to the position of the defects which carry the mobility. And they have some dynamics, which means that they cannot just diffuse freely in space. There are some rules for them to diffuse. You see that the dynamics is constrained. And if you look at what happens for the dynamics, essentially, these black regions correspond to the trace of where this mobility defect has been. So essentially the mobility went in this region, so it means that you can imagine it rearranged the liquid. So it means that in terms of my simulations, it went from blue to red. So it has a different structure. Here, the blue corresponds to the right regions, so the regions that are still at the same structure as time zero, and the black regions have moved. So you see that really what you look at in the dynamics corresponds to the trace of where the mobility has been through. So you have a point moving in space, and it draws a domain of a given size, and this is the origin of the domain. So here, this is the same in 2D. So you would have point defects, and then they can move in time. So you imagine time going down below. And if you look at the trace, then you get these domains, which are quite large. So you can get a large correlation length in the dynamics. But the statics here is completely irrelevant. Okay? So now let's look at, so you can think about this picture for now. It's really just, increasing dynamic length coming from dynamics that is simply constrained. So if we look at some recent computer simulations, so the reason why they're recent is because, and why they're different from before is thanks to the swap algorithm that I've described. So again, remember I said thanks to swap, we can actually get equilibrium samples at very low temperature. And this was not something that we could do before. So now we think, okay, we use swap just as a tool to get to low temperature. And then we use these configurations to run MD. So we know that within the MD simulations, we're not going to be able to relax the system because we've never been able to do it before. But whatever, let's just look at the dynamics. So we're looking at the equilibrium dynamics. And I showed you already a movie at low temperature, but I still want to show you what happens at high temperature. So this is the onset, so basically where the dynamics starts to become super Arrhenius. And again, this is the blue-red thing. So blue regions have the same local structure as time zero, and the reds have a completely different structure. You see at high temperature, there's no real clear correlation, or the dynamic length is very small. But if we go to a regime that was not accessible before, then you really start to see the emergence of these correlated dynamical regions. Okay? So this is what we see, and it's nice because now we can really observe the dynamics in this regime. Now this is more, I think we actually have more beer. It's not supposed to be a quiz, but if we take this configuration, thanks to the super, integrate description that Misaki said, you can actually really measure what the static correlation length is in this model at very low temperature, at these temperatures. This is roughly the scale of the static regions. So it means that in the RFOT picture, basically what you would have would be regions of that size appearing, in the extreme case, appearing independently. So basically red spots over this side, just they would appear spontaneously. Red spots appearing completely randomly, and this would be the RFOT, but like really taken stricto sensu without taking into account the space. So I think, well, maybe. Does someone want to comment on the size of the static correlation length and the size of the dynamic correlation length? Is it clear that it's RFOT or it's something completely facilitated? Alberto wants to say. So if we look at the length scale here in the dynamics, let's say when it's here, is it like the zones that have relaxed, are they much larger, much smaller? Does it look like regions of this side popping independently or something different? I don't know. What do you? Alberto has something to say. Yes, indeed. Alberto wins a beer. Indeed, the dynamic correlation length is much larger than the static one. So there is something going on, and okay, maybe we've been a bit extreme, but now we can really measure that. So this is the dynamic correlation length, and this is the static correlation length that Misaki was talking about. So this is thermodynamics, and this is the dynamics. And you see that as you go to lower and lower temperature, actually it seems like the two are getting more and more different. So if you imagine that the dynamics is becoming slow because this length scale is increasing, then it actually seems like the dynamic length scale has something more to it than just the increase of that. So still an open question at the moment. So there's a lot of debate, a lot of question as to whether actually this thermodynamic length increasing drives the relaxation, or if there's something more, and Misaki will discuss other ingredients that might happen. Yes, Sharon.
What kind of behavior do you get for this dynamic length scale? How do you measure it in one of these ideal gas of defect-like kinetic constraint models?
You get something very similar to what we observe.
Okay.
Yes, so you get growing dynamic length scale, you get super Arrhenius, you get basically everything you're looking for. A lot that you're looking for. You don't get the point to set, which if you do the construction, Misaki did it, other people did it, you find it. Sorry, okay. The point, what I say point to set is static length scale, sorry. Sorry. So now Misaki will explain. Yes.
Some hypothesis. Okay, so Camille explained that naive RFOT scenario means something, and facilitation is important. And this dynamical facilitation ideas comes from some abstract ideal gas-like model. Let's say physical interpretation is quite difficult. It's quite abstract. So we wish to understand, okay, we now understand from your simulation, facilitation is important. Then we want to understand what is the physical mechanism causing this facilitation mechanism. Therefore, now we are going to discuss facilitation induced by elasticity. Elasticity is a property of material, and consequent avalanche type of motion in relaxation. So actually this part is related to also tightly connected to Albert. So elasticity is well defined. The facilitation is floppy, but something propagate and accelerate the dynamics. I will explain. Or you have a better.
I missed that part. So I should have explained that the idea with the mobility effect moving corresponds in the simulation. It basically means that if you have mobility in some region at one time, it will facilitate or help the neighboring region to move. So this is really what you have in the KCM. But as such, I agree that it's very ill-defined. But at least I thought I should explain what facilitation is. It's like you have mobility spreading in your system.
So the point is there a kind of definition that allows you to sort of distinguish what's going on from something in a complex energy landscape? The point of facilitation, as you said, is that energy shouldn't matter. It's just you have those obstacles and those things. But this is, in the context of facilitated model is clear. But then if you go back to the real thing, it's not clear anymore. At least to me, what is that?
No, I think as Misaki says, it's ill-defined. I think one way to see it is you have mobility that spreads in the system. So this is like if you move somewhere, it helps the neighboring, so it gradually eats. But otherwise, it's not clear. So Misaki will put maybe
We will come back to
more
this issue.
physics into
Okay.
facilitation. Yeah.
Okay, so I mentioned that elasticity, well, as a working hypothesis, elasticity play an important role. So, okay, as I mentioned that there are many different theoretical scenarios trying to understand Glassy dynamics, including dynamical heterogeneity. So roughly speaking, so we can classify different theory into, let's say, two paradigms. So it's not accurate, but let's say we can characterize them, classify them into two directions. So one is, let's say, viscous fluid paradigm. So majority of theory, for example, mode coupling theory, it describes glass-forming liquid starting from liquid side as a reference and trying to understand low temperature liquid as extremely viscous fluid. But on the other hand, some people like Joppe Dure and L. Metal, they are trying to understand supercooled liquid starting from solid side. That is called solid dot flow paradigm, let's say. So in this, in the next 15 minutes, I'm going to explain this paradigm, solid dot flow. Okay. So the reason is that recently there are many interesting numerical simulation showing, in favor of the presence of elasticity and plasticity in liquid. So I need to explain that elasticity and plasticity is usually the concept developed in solid mechanics. But now we are trying to use them for liquids, okay? So it's not trivial things. So as you can see that, so recent simulation show that elasticity and long-range stress correlation appear at low temperature supercooled liquid. I'm not going to explain in detail. On the other hand, the group of Damien van der Boog and Sylvain Patinet, they find that so the local rearrangement of particles looks like a plastic activity or shear transformation zone that has been observed in the solid mechanics. Okay? So they observe rearrangement in liquid, but the rearrangement are very similar to plasticity and shear transformation in solid. Okay, to conclude, there are many supporting evidence that elasticity and plasticity are important in liquid. From this numerical observation, one can draw the following picture. Okay. Suppose that you have a local rearrangement, let's say plastic event induced by thermal fluctuation in liquid. So this event induces elastic interaction, so similar to solid. And because of this elastic interaction, other sites at nearby region show plastic events. Then these induced plastic events again induce other plastic event at the neighbor region, okay, making a sort of cascade or avalanche type of event that can be interpreted as facilitation that we saw in the computer simulation. Okay. So this is just a picture drawn by hand. So we wish to implement this in computer. Okay. Okay, so we want to implement that picture on computer. To this end, we use so-called elastoplastic model that Alberto and Elizabeth introduced yesterday. So basically, so this is a sort of coarse-grained, mesoscopic, lattice-based modeling. So each site would correspond to a bunch of particles, molecular simulation of particle. Actually, there are many variations of model, many different type of rules, but we use very simple setting, just a local thermal activation plus elastic interaction. So we don't think this is really realistic model for glass forming liquid. Instead, we ask, so we just take two ingredients, then we ask what we can get, what we can explain. So this is a movie. So the red site corresponds to the mobile site, and the blue site corresponds to the immobile site. So you can see sort of a propagation of event that we can interpret as a facilitation mechanism. You see? So this is a larger qualitative picture. Also, we can measure quantitatively the 4-point correlation function. Again, in order to characterize dynamical heterogeneity, we need to quantify the variance, fluctuation of dynamics. Since dynamics is described by 2-point time correlation function, the fluctuation of dynamics is quantified by 4-point correlation function. So our elastoplastic model successfully reproduces the temperature and the time evolution of Chi4 compared with the real molecular simulation data. Okay. And also, we look at the peak value of Chi4 that corresponds to the size of dynamically correlated region, and we plot this as a function of relaxation time, because this plot is inspired by real experimental observation or estimation. First, we perform simulation for the model without elasticity. So no elasticity, just a thermal activation. In that case, Chi4 peak doesn't grow at all. Okay, no dynamical heterogeneity. But if you switch on elasticity, we see the growth of Chi4, growth of dynamical heterogeneity. So it means that at least within this simple model, the elasticity causes growing dynamical heterogeneity or facilitation. So we studied more about along this line of thought. So in the end, we conclude that so within this scenario, so dynamical heterogeneity is sort of avalanche type of motion, but it's a bit different from standard of avalanche having the system spanning system expanding rearrangement. Because of finite temperature thermal effect, the growth of avalanche is cut off. And this size is nothing but dynamical correlation length. Okay, so this is the, let's say, the thermal avalanche scenario, and we are happy if this is also related to what Alberto mentioned yesterday in the case of.
Again, so what you are saying is that this is not related to the energy barrier that.
So in our model setting, we don't have a energy barrier, so if you plot the relaxation term, it's purely Arrhenius. But it's just a model, but in order to reproduce non-Arrhenius behavior, we need to elaborate a model. For example, temperature dependence of energy barrier. So you know that the elastoplastic model has many arbitrariness and rule, right? So yeah, but this is within this model. But okay, so this is open question. Okay, so this is avalanche-like picture of dynamical heterogeneity looks cool. Okay, but maybe we miss something. Okay, so if you carefully look at time evolution of dynamical heterogeneity in the Camille data, actually dynamical heterogeneity is more like a coarsening process. At high temperature, actually it looks like avalanche, but with decreasing temperature where she explored by swap Monte Carlo simulation, time evolution looks like a coarsening. So it's a sort of gradual growth of domain between the slow and the mobile part. So this is sort of open discussion. We need to understand better. Do you have some comment?
But this means that, so what is this avalanche-like or boxing-like picture is against the random first contact position. Means that it's not correct or not?
So that's a good question, I think. So in this, yeah. So as she said, random first order transition alone cannot explain all these growth, big dynamical heterogeneity. You know, if you compare the static correlation length and the dynamical heterogeneity. So we are now explaining or discussing, let's say, more larger length scale phenomena. Perhaps the elementary process, elementary local activation would be related to the collective motion of random first order transition. But yeah, so if you combine it, there's a super expert sitting next to you. So.
Yeah, maybe just as a comment, in this case, the excitation time is completely reduced, and yet you get the growing length, dynamical. So you see that, I mean, the growing length, dynamic growing length per se is not explaining, or I mean, it's not necessarily related to the growth barrier.
Yeah.
So it could be.
No, also in the creep, the avalanches are absolutely invisible from the velocity, from the relaxation time. So this is first like case when the second you see, but faster.
It could be that maybe there is a smaller landscape, the static one, which shows only the local energy, but it can also be actually the local energy given by something else. Maybe just the elastic model are changing, so it's pretty local, and so there are differences. Specifically different.
This is equilibrium. So our model doesn't satisfy detailed balance. I'm sorry. But yeah.
Not so much.
Yeah, so the model actually
It's in the steady state.
in a steady state. in a steady state, but the dynamical rule does not satisfy the detailed balance. Okay, so we have to improve more. But I can say that dynamical heterogeneity is quite a generic feature, not only supercooled liquid, but also grain and oscillation and right? So without violating detailed balance. Yeah. So if the mechanism is quite universal, maybe this our model also characterize somehow dynamical heterogeneity or super.
The problem is the top to one of the others.
This one.
Yeah, because you have to figure in your mind that the opposite of an avalanche also happens because you're in equilibrium. So if you run the film backwards, you should see inverse avalanches. These are quite hard to picture, but maybe it's simply that one shouldn't think of snow coming down the mountain because otherwise going up would be rare.
Yeah, I don't know, me neither. But
is this related to the space-time tubes of moving?
Well, yes, if you're in equilibrium, the film you can pass it backwards and it's equally good. So you should see.
So in your case, Misaki, if you look at space-time, you have a cone of activity that spreads, but you don't have like the opposite.
no, I don't see.
But in principle, you could. It should happen.
Yeah.
In the model, it could.
No, in this model,
No, it's not in the model.
but in principle, one could have an avalanche.
Yeah.
Take a piece of paper and crumple it. Maybe it's like an avalanche, or is it not? And then you pull it back, so it's like a reverse avalanche, right?
Because paper is in equilibrium in a liquid, it will spontaneously. It should crumple and uncrumple at the same.
Okay.
So these avalanches are like happening every some time, right? Propagates.
Yeah.
And it's right, I don't know, just an idea looking at the distribution of the time between the avalanches.
Yeah.
Let's say something.
Yeah. We didn't see the time between avalanche, but if you measure the size of avalanche, okay, it shows power law, typical power law decay, and with some cutoff due to finite size effect. But on top of that, because of finite temperature, so we have an additional cutoff due to finite temperature fluctuation. Okay, so how much time? Okay, so I just go very fast, maybe 5 minutes. Okay, so because many people are working on a machine learning, so we briefly explain the current status about the machine learning grasses. So we have two subsections. The first one is prediction of grassy dynamics from snapshot. Okay. The second one is fast Monte Carlo sampling assisted by machine learning. Okay, so the first one, so this schematic picture is taken from a recent sort of review paper. So the goal is to predict future grassy dynamics, including dynamical heterogeneity, by just looking at snapshot structure, where you don't find any particular pattern by just looking at the eye. But hopefully machine learning can do this very difficult job. Okay. So indeed, people do training a machine, for example, support vector machine, graph neural network, multi-layer perceptron, etc., etc. So using data, then they predict dynamical heterogeneity of unseen data, test data. Okay.
So how deterministic is it, the dynamics? Like if
Yeah, very, very good point. The setup is as follows. So you have a given static structure, right? Then you assign the velocity by Maxwell-Boltzmann distribution because it's in equilibrium. But not just once, but you assign velocity many times, let's say 100 times. And the very interesting point is that if you look at the statistics of mobility by initial velocity distribution, you see heterogeneous dynamics. So this is sort of ensemble of statistics of mobility, sort of. That is called the propensity map. And in this business, people try to predict this mobility map. Okay, so this is just a bit of a broader perspective. First, people prepare trajectory data by molecular dynamics simulation. Then, from this trajectory data, people analyze dynamical data like mobility map that I showed in the previous slide, mobile region and immobile region, etc. On the other hand, we can compute structural data, purely structural quantity like, I don't know, angular part or radial part, etc., etc. And for the supervised learning part, so the prediction of dynamics, we use both dynamical data and structural data. Okay. So supervised means that we use dynamical data. Then we can perform regression, prediction of this using structural dynamical data. And also we can do classification. Now you can classify mobile and immobile particle. This is supervised learning part. On the other hand, we can do unsupervised learning in a sense that we don't use dynamical data. So we just use structural data. Then we try to identify relevant structure. For example, structure having large fluctuation, etc., etc. Okay. Here I explain just one recent supervised learning research by Giulio and Gerhard and Ludovic. So I don't go into detail, but anyway, so on the left, I show the result from molecular dynamic simulation. So this is ground truth. On the right, I show the prediction by multi-layer perceptron. Actually, it produces quite well. Also, they predict the time evolution of 4-point correlation function chi4, and it matches very well. Okay. So this is a very good job. So open question, open discussion would be, okay, so according to the current cutting edge machine learning study, so people reproduce dynamical heterogeneity with the accuracy, let's say, 80% in the correlation coefficient. I think this is quite remarkable, but question is, what does it mean? So in terms of theoretical scenario of glass transition. Of course, by using the most accurate theories, that is mode coupling theory, it cannot predict at all this kind of things. It completely fails. But machine learning can predict very well with 80% by using just a static structure. So what does it mean? What does it mean? So the remaining 20%, does it correspond to some dynamical effect? So this can be an open discussion. Yeah.
And if you want to go to shorter or longer times, you have to retrain on a different pace.
Okay, so we are tired, so we can go. Okay, just 3 minutes. Okay, the last part is first Monte Carlo sampling part. To this end, I need to explain so-called generative modeling by using the data set of Hollywood celebrities. So in this generative model setting, starting from these training data set, so we wish to learn the underlying probability distribution, okay? By using your favorite machine learning algorithm. So this is quite a difficult task, but you can do it. Once you construct underlying distribution, you can generate data that does not exist in the original training data set. So you can create a new image, new face that does not exist in the world. Okay. So this generative modeling is very popular nowadays, as one can see ChatGPT, etc., etc.
Misaki, are they real celebrities?
I don't know. The, beautiful. Beautiful face.
That's what the model does.
Yeah, maybe.
Maybe it's the generous.
Maybe.
It's like your collaborators.
Ah, yes. Okay, so we want to do physics data instead of Hollywood celebrities. Okay, so we can do similar to the previous example. So we can learn the underlying probability distribution and in a clever way. And then we can generate new sample, new configuration in an efficient way. So I'm not going into detail, but this is basically generative modeling approach. Okay, so here I show 3 recent studies.
About the generating data from a model, but it is like a fixed disorder or I mean,
Fix
parameters of the model are changing through the training or always the same?
model, yeah, you given model, then you do training. And during training, the parameter in the model changes, but you want to find the optimal value of a parameter.
I mean, the forming of Hamiltonian.
Yeah, okay, so many different studies. So one good way is that you can decompose this probability distribution by some clever way, like some factorizing into different length scale or some recursive structure, some clever way. Once you train the Hamiltonian in that way, you can easily generate.
I think the question is if you do a system like Glass, but
Okay. Okay. Thank you very much. Okay, yeah. So actually, the most of the recent study use a relatively simple model like FIFO, Ising model, second order phase transition. But then, yeah, disorder model is quite open, and it's a very hot topic, and I'm going to explain. Okay, so the first paper by a group of Waite and Zamponi. So this is a shocking, so this is a paper title which is shocking. So machine learning assisted Monte Carlo fails at sampling computationally hard problem. So computationally hard problem means Glassy system like we are doing. So they conclude that it doesn't help well. But this is the paper in 2023. How about 2024? Okay. So, okay, this is again the paper by Gerhardt, Giulio, and Ludovic. They use normalizing flow, which is one popular generative modeling approach that generate low temperature configuration from high temperature configuration. Okay, so this is a sort of relaxation time as a function of inverse temperature. So this is MD result. Okay, so the relaxation time increases quickly. Okay, but then this normalizing flow method is much faster than molecular dynamics, and they can explore a much lower temperature. So this is good news, but still, compared with swap Monte Carlo simulation that Camille said, it's still much slower than swap Monte Carlo. Okay, so this is the result. But two weeks ago, the group of Kosorovic put a very nice paper on arXiv about discovering optimal Monte Carlo movement by using reinforcement learning. So the goal is to find like a swap-like displacement by using machine learning technique. So actually the first author, Leonardo Galliano, is here, and he will talk about this tomorrow in the poster session, so we can listen this. Okay. Thank you. Finish.